So hey guys, today we are going to talk about another research paper, that is differential transform. In the previous research paper, we were talking about selective attention, and I mentioned that maybe in the next video is going to be about differential transformer. So yeah, this paper has been released by Microsoft Research in the Singular University. Now, what is this paper exactly about? They have cleared this in the very first line, that transformer tends to over-allocate attention to irrelevant context. So I know a lot of you would be saying that this is something similar to what we were seeing in the attention mechanism that we modified in the last paper, that was the selective attention. And now this paper also we are going to talk about this irrelevant context. But yeah, this is how you improve a method, right? You improve a particular method like attention by doing a bunch of experiments on it, a lot of different patterns you detect, and then you make some improvements, then you come up with some final outcome, right? So what are they saying? Specifically, the differential attention mechanism calculates attention score as the difference between two separate softmax attention maps. The subtraction cancels the noise, promoting the emergence of sparse attention patterns, right? So by being less distracted by irrelevant context, the differential transformer can mitigate hallucination in question answering and text summarization. So yeah, we are every time trying to make sure that the irrelevant context thing is not happening in our case, because we want, whenever we are doing a, let's say, retrieval part using that needle in a haystack thing, or we are doing some summarization part, we want the things to be accurate and focusing on the exact thing that is needed, not irrelevant context, right? Now, what are they saying? At the they have in the current with decoder only transformer emerging as the de facto standard for LLMs. At the heart of transformer is the attention mechanism, which employs the softmax function to weight the importance of various tokens in a sequence. We all already know, when yesterday we were talking about that how attention and everything works. And let's, for this case, I'll again write the formula to make sure that you guys remember it. So you have we have the attention formula here. Let's write it here. The attention, right? So what it is? So you have the softmax, right? You have the query, the transpose of key, then you have the dimension here, and then you have the value. Simple as that, right? So this is the current attention formula. Now, we usually modify things in here only, but let's first understand what the paper is trying to tell us, right? They are saying of this particular diagram, we visualize normalized attention score assigned to different parts of the context by a transformer. The task is to retrieve an answer embedded in the middle of a pile of documents. Sort of they're conducting that needle in a haystack solution, sort of that. Now, the visualization reveals that transformer tends to allocate only a small proportion of attention score to the correct answer, while focusing on irrelevant context. Here you can see, right? If you see that this is the context, this is the main answer. And in the main answer, the ratio is only 0.03. Whereas it's 0.18 on the attention noise here and 0.34 on the irrelevant context here. So they are saying that whatever thing which is not required, we are calling it attention noise, right? We term this useless attention score, you can sort of say, as attention noise. Now similarly, when they are applying this differential transformer, the work that they are proposing in this paper, you will see this rise almost 10 times, from 0.03 to 0.31. And similarly, the attention noise is going from 0.18 to 0.01, 0.34 to 0.01. That is around 100% decrease also in the in the attention noise. So this is helping us a lot. Similarly, if you see the accuracy percentage which they are mentioning, you will see that differential transformer is 85% and transformer is only 55%. So we can see a very major difference when it comes to the accuracy and the attention score that is being assigned to the correct answer, right? So yeah, let's move to the next part. They've specifically mentioned here that we partition the query and key vector into two groups and compute two separate softmax attention maps. Simple as that. Then the result of subtracting these two maps is regarded as attention scores. The differential attention mechanism eliminates the attention noise, encourages the models to focus on critical information. So this approach is analogous to noise cancelling headphones and amplifiers. So anyone, I think, who has been working on attention now will be able to understand that, okay, this is something not they have tried first time. A similar approach, not exactly this, but a similar approach was tried, I think, few months back. I was reading one paper, I don't remember the name exactly, But yeah, they were doing sort of similar thing. They were trying to calculate that how exactly we can remove that particular noise from there using some difference between two grouping, right? So I think they have come up with a better solution than the result of subtracting, right? So what you are going to do? You are going to divide this query into maybe Q1, Q2, and what are they saying? This K equals to K1 and K2, right? And then you're going to have a separate function for both of them for these two groups, and then you're going to have a subtraction, and then you're going to get the softmax out of it. Cool. Okay. And the thing which they are saying here, that they have got this from an inspiration from noise cancelling headphones and differential amplifiers in electrical engineering. So I think 1 month back, one of my AI engineer friend told me that CNN was also inspired from this electrical instruments. I don't exactly remember the context, but yeah, it was something similar. So it's really good when you figure out, okay, that these fields and the working process internally of when we are working on similar scale things, they also tend to, correlate in some or other manner, right? Now, what are they saying? The scaling curves indicate that differential transformer are only about 65% of model size or training tokens needed by an original transformer to achieve comparable language modeling performance. It's a big thing. You only need 65% of the original one. So yeah, let's figure out how they're going to do that. So I think we are now coming to the mathematical part. The model is stacked with L differential transformer layers. Given an input X, that is X2 n, we pack the input embeddings into X0. And this is simple as that, where the dimension represents the hidden dimension of the model. The input is further contextualized. So I think this is very straightforward. They are saying we also adopt a pre-normal RMS normalization and Swiglu as improvements following in Llama. So okay, they are taking inspiration from Llama. That's a good thing. Now, what are they doing here? As we were discussing already above, that I'll take the pen here to make sure things are. So we were already discussing, right, that from the attention that we had this softmax of QKT, right? So what they are going to do? You have the softmax of QKT, right? DK and V, right? So I'll change the color for making things easier here. Cool. Now, if you see, we are dividing, like having two things here, because they were already mentioning that we partition the query and key vectors into two groups and compute two separate softmax attention maps, right? So you have got the query divided into two. Similarly, you have the keys also getting divided into two. The value is going to remain same. The value will remain same, and then you will have the difference here, right? The softmax of this and this. The query 1 Q1, query 2 Q2, and the dimensions remain same and the value remains same. Now this lambda here is a learnable scalar, what they're saying. And in order to synchronize the learning dynamics, we reparameterize the scalar lambda as exponential of query Q1, the lambda value, minus exponential of that same thing. And you will have this initial part of lambda, right? So these all are learnable parameters, what they're saying. And is a constant use, this initialized is a constant use for initialization of lambda. So I think randomness plays a very big role here, right? So they are saying that we empirically find that the initialization is 0.8 minus 0.6 into exponential of 0.3 into L minus 1 works well in a practice. So L is 1 to L, representing the layer index, obviously. So you already have the value for lambda initialization also here. So you can directly use this here. Cool. Now, when coming to code is simple as that. Code is not at all complex. If you see, we have we are getting the query queue and the key values from here. The splitting, we are partitioning into two, and then we are calculating the value. And once we calculate the S, things are really simple. We are attention 1, attention 2, and then we are getting the softmax for this along with lambda and multiplying it with V. So simple as that. Similarly, for multi-head, we are doing the same thing. We are just concatenating the heads, right? Because that is what we do. What are they doing here? If you see here, everything remains same. The overall formula, okay, I every time choose this. The overall formula for multi-head remains same. We are concatenating the heads from this to this. The only difference is this lambda initialization that we are doing here, and that we have already talked about above because it's a learnable parameter, right? And what they are saying that this is the constant scalar in equation 2, where this is a learnable projection matrix and using the RMS normalization, right? So yeah, so we use a fixed multiplier 1 minus lambda initial as the scale of linear rate. 2 align the gradients with transformer. So the learning rate, and when you're talking about above, we already talked about the formula that these guys have already proposed, so that can be used, right? So yeah, so overall architecture looks something like this. We have L layers stacked together, where each layer contains a multi-head differential attention module and a feed-forward neural network, right? So yeah, simple as that. Now these all mathematics I think we already know from the transformers attention is all you need paper. Now for the experiments that they have done, they have used a 3 billion size differential language model on 1 trillion tokens and compared with previously well-trained models in various downstream tasks. So let's directly go to the results, and you can see here this is the stable LM, and this is the stable LM that has been used for 1 trillion tokens. For this we already have results for ARC and maybe Vinograd. Okay, cool. So average we don't have for this. So for differential 3 billion, we are getting the highest results every time. You can see the highest results. But one curious thing was that maybe for 1 trillion tokens, stable LN is also competing in this PIQA. Yeah. So maybe in the other ones, if the results were there, it could have been good. So what are they showing here? That the differential transformer 3 billion is literally able to outperform the OpenLlama 3 billion version 2 by 5 to 6%. And you can see this difference of 5 to 6% almost every time in all the cases, right? 5 to 6% is almost every time there. So this PQ, maybe it's a bit difficult benchmark they are trying to show. Now the scaling model size range you can see here, 38% fewer parameters as we were discussing. Here also you can see 36% fewer tokens, because for reaching this place you will have to reach this one according to the original one, right? So what can we conclude from here? The differential transformer only requires 65% of model size or training tokens to match the original transformer performance. Big thing, right? Really big thing. Now, according to the fitted curves, what are they saying? It's 6.8 billion size transformer achieves a validation loss compared to 11 billion transformer requiring only 62.2% parameters. Similarly, for 7.8 billion and matches the performance of 13.1 billion, that is requiring only 59.5%. So you see here, not only using this equation we are getting better results, but let's suppose due to some constraints we are not able to get a model of, let's say, 13 billion, right? 13.1 billion, which they have mentioned here, I think. Yeah, the 13.1 billion, the 7.8 billion is already matching the performance of the 13.1 billion transformer model. So literally this can fit in 810 GPUs, I think 4 810 GPUs, right? But I don't think this one can fit. So anyone who is working on maybe has some constraints over GPU sizes and memory allocations, this can help a lot, right? So I think, and I was playing with this 7 billion one, I used 4 8 GPUs, I remember. Yeah. So coming to scaling training tokens, they say that the transformers achieves comparable performance as transformer trained on 351 billion with 161 billion. Just see guys, 63.7% difference is there. It's a very huge difference. Because 63% less tokens you have to train and you are still getting the same results. Similarly, for long context evaluation, this can help the RAC people a lot. That evaluation is conducted on book data within 64K length, because they have extended the 3 billion language model size to 64K length context. Okay, so they are saying differential transformer achieves a lower NLL values than transformer, because lower than NLL values, better it performs, and differential is better. You can see here clear difference here, right? Similarly, the needle in the haystack solution is there. Needle in a haystack, right? This problem is there. So here you can see clear difference. In the worst case, you can see 0.6 and 0.04. That's the difference you have between a transformer and a differential transformer. They are saying that we find both models good accuracy for n is equals to 1. What is n here? The n is equals to 1, 2, 3, 4, 6 needles into 4K context length with retriever 1 to 2 needles. So you can see a clear winning of differential transformer over transformer. Because guys, what was the overall motive, right? What was the overall motive? What they have mentioned here. Transformer tends to over allocate attention to irrelevant context, and that we are figuring out here, right? We are getting 0.032 to 0.19, right? Oh, this is okay, fine. Beginning of sentence token, this is something from 0.18 to 0.01. From 0.03 we are getting 0.31. That's a huge difference, and that's the reason that we are seeing the benchmarks, right? So yeah, attention score analysis, you can see still far better. Obviously we were expecting this, we already saw this in the initial diagram. In context learning, you are going to see the same results that we are tending to outperform one. Summarization, differential transformer is still outperforming the other models because it's free of hallucination, right? Free of hallucination. And for this they have used the model output along with ground truth responses to GPT-4o. So you can't say that this can be biased. So differential transformer is still outperforming the normal transformer in case of hallucination, right? Hallucination evaluation. So this will help a lot to drag people who don't want the model to hallucinate, right? Similarly, for retention logits, you're going to see a clear difference here, hidden states and everything. Now, attention outliers and everything. Ablation study, I will leave it on you guys. You guys can go and read. What are they mentioning in the conclusion? Differential transformer which amplifies attention to relevant context while cancelling noise. Experiment results on language modeling show that differential transformer outperforms transformer in terms of scaling properties, long context. So I think almost everything they have covered. Scaling properties, long context, modeling, key information retrieval, hallucination mitigation, in context learning and reduction of activation outliers. Okay. So yeah, the findings propose this and the attention pattern becomes much sparser. We would also like to utilize the property to compress key value caches. Oh, this is going to help a lot. So yeah. Now we would like to acknowledge, okay, when handling for maintaining the GPU cluster, the long sequence training utilizes Q, which is an internal version of, okay, good. So I think appendix part, you guys can go and read. They have implementation of the differential transformer. The same thing that we were already talking about above. They've also done it with flash attention. Efficiency training is there, that forward plus backward throughput and throughput everything. So yeah, that was overall it for this video, guys. I hope you guys learned something new from this, and maybe we will come up with another research paper in the next video that is going to be about the evaluation that we are doing nowadays. How is it biased? How is it sort of biased? Cool. We are going to talk about it. Cool, guys. Thank you and have a nice day.